Hello and welcome back to the second podcast of week 4. Our focus today is on another way that we can do calculations based upon solutions. Now, we've got a couple new definitions that come along with this one and a new formula for you to use as well. Okay, so first things first, our dilution is our main thing that we're looking at today. And with dilutions, there we go. We're looking at exactly what the word sounds like. You are adding a solvent, in this case we'll be focused on water, of course, in order to dilute it. And I mean, this is nothing new. Think about when you make iced tea or something and you make it way too strong and it's sweet and kind of nasty. What do? You add a little bit more water and it's diluted and it can taste better. Okay. Now, standard solution is a word that we've talked about I think the week before. And ultimately, if you have a standard solution, it's a solution whose concentration is known. Now, if you know what the concentration is, then you're able to ultimately work with it and do things with it. Because a more concentrated solution has more actual molecules, cations and anions to potentially react with something else, right? So concentration, don't forget, when we talk about molar concentration, is moles per liter. So more concentrated means more moles dissolved into a given volume. All right, continuing on, if we continue to consider what dilution means, we are adding a solvent, which, like I said, in this case, we're focused on water, and the purpose of adding it is to lower the concentration. We will be entirely focused on aqueous solutions, so water, like I mentioned, to dilute. And ultimately, the amount of stuff that is actually dissolved, that doesn't change. So if you can almost visualize this, if I have a container and I have, say, this is the equivalent of 1 mole of something in the bottom, and then I add water up to here. Oh, okay, no big deal. But what if I have the same container and the same amount of solute in there, and instead I add water up to here? All that means is that this one is more dilute, right? I have more overall volume. The actual amount of what's been originally put in there, though, is the same. Okay, let's keep going. Now, since the amount, meaning N, right, the amount of solute remains constant, we have kind of a cool relationship that exists. Now, again, think back to this. The amount, how much was dissolved, is the same. What changed was the volume of the solvent added. So that means that N, the amount we start with, is exactly equal to the amount we finish with. There's no difference between those two. Go back, consider our concentration formula. Concentration is equal to N over V. Well, if I rearrange this so that I've got N by itself, then I have N is equal to C times V. Well, if this is what the first amount is equal to, which is identical to the second amount, that's ultimately all we're doing. We can take this and think of it as being N1. Take this, think of it as being N2, and remember, original concentration, original volume, final concentration, final volume, we get this brand new, wonderful dilution equation. And within the context of this equation, the actual variables are pretty logical. C1 is going to be our initial concentration. And concentration, of course, is in moles per a liter. No difference there. Our V1 is going to be our initial, or you can think of it as your starting, but our initial volume. And your initial volume is going to be in liters. Important for this one, guys, to honestly, it could be in milliliters too, but just to make sure whatever V1 is, V2 is consistently, so that final volume is in the same units, so liters or mils. Just stay consistent. C2, of course, is going to be our final concentration. And again, moles per liter. Alrighty, these are actually fairly simple equations. The biggest thing to remember with these is not getting mixed up in the context of the question with what you've been given. And I'll walk you through a few of them. Another type of definition first though, stock solution. This is a new one. Really important that you know it because it's going to be referred to quite a bit in questions. Ultimately, it's just going to be whatever solution is the most concentrated. And it's the solution from a dilution perspective that we start with. So the one that is being diluted. When I say it's generally a standard solution, I mean that you know the concentration. That's the definition of that standard solution. Now, we go through the process of dilution pretty carefully, and unfortunately, I can't do this with you. We would have done it in class, but I'll get you this week to kind of watch a bit of a simulation on it and comment on it. Now, ultimately, we take a full strength stock solution first, and then we take a little tiny bit of it. Let's take 1 mil, for example, and then we put it into a new test tube. And with that new test tube, we add an extra 9 mils. So that means that in total in here, there'd be 10 mils. Oh, which is the same as what we had here. But it's been diluted because we only used 1/10 of the original. And then we can keep going. We can take 1 mil of the second solution and add it to 9 mils of water and da-da-da-da, we have decreased the concentration again. Notice we just keep on going, and with all of these, the concentration continually becomes less. This is dilution. It's called a serial dilution because you do it over and over and over again. And the point is to make different concentrations of different solutions where they are all standard solutions, where you know the concentration of each one. All right, question-wise, check it out. These are a little easier, truly. You don't have to spend a whole bunch of time thinking about formulas of your different compounds, playing around with molar masses. Show you what I mean. So first things first, pay close attention to your givens. We have 300 mils. Notice the mils. That means this is for sure volume. This has been added to 172 mils, or sorry, 17.2 mils. Oh, that's weird. Another volume. Hint, hint that this is dilution. And we are adding it to a 5.14 mole per liter. Pay attention to those units. Moles per liter tells you it's a concentration of hydrobromic acid. Ooh, check it out. We haven't done an acid in a little while. Okay, calculate the resulting concentration. Whew. So you have to figure out here, what do you start with and what do you finish with? If we're looking for a resulting concentration, then that means that we're looking for another C value. We have 2 V's, we have 2 C's. Absolutely, this is a dilution question. So I always start these by writing down my givens. It's really, really hard to do questions like this if you don't write down what you know and make sure that you organize it properly. So this is key. You have to have your givens down. I will be looking for them in every single question. Okay, the first volume. Well, read carefully. I take 300 mils and I add it to 17.2. That means I'm starting with 17.2 mils. And then I'm adding an extra 300 mils to it. I'm starting, that's that V1, 17.2 mils. Okay, V2 is not 300. I am adding an extra 300 mils. So that means that both of these together is actually V2. So add them together, 300 mils plus 17.2 mils, we have a total of 317.2 milliliters. Okay. Now, my initial concentration is what I start with. It is my original volume of 17.2 mils with my original concentration of 5.14 moles per liter. The whole point of the question is to find the resulting concentration, in other words, C2. Okay, let's go into how to do this. you have to go back to that new formula. So you've got another formula in your arsenal of things to use. This is C1 times V1 is equal to C2 times V2. Now focus on what your goal of the question is. We're looking for C2, so don't get lost. If that's what you're looking for, then be careful that you have to isolate it properly. How do you get rid of a times V2? You divide by it. We do to one side of the equation, you have to do to the other. These are gone. There's your equation, folks. Be careful that you have the right values on the top and the correct value on the bottom. C2 is equal to, okay, I put C1 in, 5.14 moles per liter times V1, 17.2 milliliters, divided by my second volume, 317.2 milliliters. And notice what's happening with the units. Milliliters and milliliters cancel out. We will get an answer as a moles per liter concentration, which that's exactly what we want. And I can write it as a concentration. It is the new concentration of HBr, hydrobromic acid, okay, is equal to, I need 3 sig digs, 0.279 mole per liter. And there, whoop, it is. Okay, new formula, but notice really less steps going on. I didn't need to play around with molar mass. I didn't have to use more than one formula. I just have to pay close attention to my wording. Okay, let's check out another one here. All right, for class experiment, a teacher must prepare. So think about that. That is the goal. The goal is to make this volume of this, maybe I'll switch to green here, actual concentration of sulfuric acid. Okay, that's the goal. Now, how is this done? Well, the acid is usually sold as this concentration. Notice something, guys. This is a way higher value. Guaranteed then that is the stock solution, which means that is my original concentration, 17.8 moles per liter. This is a huge hint to you. The C1, the original concentration, is always going to be higher. That's the whole point of what we're doing. We're trying to dilute something, which means that lower number, the 0.170 moles per liter, has to be C2 because it is a lower concentration. Okay, remember our goal is to prepare 1.00 liters. In other words, these two values go together, so make sure they're V2, C2. And we want to know how much of the original solution do we need. In terms of the importance of this, whenever I make a solution in the lab and it's dealing with a concentrated acid, this is how it's done. We have great big glass containers of highly concentrated stock solutions of acids. And when I make an acid for us to use for a lab purpose, I dilute it. How do I do it? Well, honestly, guys, I use this formula, C1V1 equals C2V2. The big concentrated bottles of acid come with their original molarity, and I then need to dilute it to get the concentration that I want. All right, so goal here is to figure out what V1 is. So we're trying to isolate this V1, work through the process, get rid of the C1, so divide it out on both sides. It cancels out here. Here is the formula to use. Always do that carefully. If you mess it up, then your numbers aren't going to work and you're suddenly taking an easy question and getting wrong answers. 0.170 moles per liter times the volume V2, 1.00 liters. That whole thing is going to be divided by C1, 17.8 moles per liter. Pay attention to units here. Moles per liter cancel out. Liters is left over. So in this particular question, our final volume is going to be in liters. And we end up with quite a small number, 0.00955 liters. So I'm going to take that and put it into scientific notation. Notice that my decimal place moves 1, 2, 3 spots to the right. If it moves to the right, I'm going to use a negative exponent. So 9.55 times 10 to the negative 3 liters is our V1. Okay? Woo, go away. And there it is. All right. Last question for you as an example. Then you can start working on the homework. Look at this one. Again, hardest thing with these is pay close attention to what the actual numbers are telling you. 30 mils, that's a volume, milliliters, of stock solution. This will be the more concentrated one. Is going to get diluted to have a total volume of 500 mils. Okay, so you've got two V's here, a V1 and a V2. The dilute solution is analyzed and it has this concentration. Some wonky units are happening here. Millimoles, and catch that, be careful. Now there's a little bit of a new terminology here. It says, what is the molarity of the stock solution? A little hint to you, molarity means concentration, but it's very specific. It has to be in moles per liter, which means this question is telling you that when we had the original concentration of that stock solution, the question wants it to be in moles per a liter, which means that C2 of 15.8 millimoles per liter is going to have to be converted. How do we do that again? Well, notice the little m. I can replace that with the proper way to do our conversion. So little m means 10 to the negative 3. So I take 15.8 times 10 to the negative 3 moles per liter. And there, we've just converted it. All right, V1 was 30.0 mils. V2 is 500.0 mils. I don't need to convert these to liters. I know it seems weird, but ultimately, as long as the units are consistent between the volumes, they'll work out and they'll cancel out properly. Okay, let's do this. C1 V1 equals C2 V2. Whole point of the question is to find our C1. That means that I have to get it by itself. So divide by V1 on both sides. Those cancel out. And I know C1 is equal to this. Here we go. Always include units. 15.8 times 10 to the negative 3 moles per liter times V2, which is 500 mils. Sorry, I'm running out of room here. Divided by my V1, 30.0 mils. Notice what I said about units. The mils cancel out, so we're good. We're left with units of moles per liter for our concentration, which is exactly what we want because we need molarity. Final concentration of calcium chloride solution is going to be, we need 3 sig digs because of our original numbers, 0.263 moles per liter. All right, and there you have it, folks. Dilution questions and how it relates to concentration. New formula, but in the world of formulas, it's not so bad. There are, did I want to do this question? No, sorry. That's another example that we are not going to do. True. Here we go. Okay. Homework. I want you to work on, please, number 6, 7, 8, and 9 in your weekly assignment. So you have 4 more questions that you can do before you move on to the next podcast. Have a good day, guys.